Hello class. In lesson 3.7, solving exponential equations, you'll learn to solve the exponential equation by using the one-to-one property, and you'll also learn to solve these equations by using natural logarithms, the inverse of exponential equations. So let's look at the one-to-one property. The one-to-one property states that for any base b greater than 0, not equal to 1, b to the x equals b to the y if and only if x and y are equal to each other, meaning that the exponents have to be equal to each other, and that's how we end up solving this equation using this one-to-one property. So for example, if I have 4 to the 2x minus 9 equals to 4 to the 7th power, then that means because the bases are the same, notice their bases are both 4, that means the exponents have to be the same. And therefore we end up with 2x minus 9 equals 7. And well, to solve this equation, we add 9 to both sides, divide by 2, and we end up that x equals 8. And that's your solution to your equation. Let's look at another example. For natural bases, same rule. Again, as long as the bases are the same, which in this case they are, they're the natural base, that means the exponents have to be the same. So 4x minus 1 equals 5 minus 2x. So to solve this equation, we would add the 2x to both sides. I'm sorry, that's 6x minus 1 equals 5. Add the 1 to both sides. So 6x equals 6, and when divided by 6, x equals 1. And there's your solution. Let's do a couple more examples. Now, it might not seem that the bases are the same, but we can manipulate numbers again, so we can rewrite them so they end up having the exact same base. So for example, here I have a base 2, but this is base of 1/2. Well, one of our properties for exponents is if I have a value, again a base b, and I have it raised to a positive exponent, I can flip this base, get the reciprocal of this base, and that changes the exponents to the opposite sign. So if it's positive, it changes to negative, and if it's negative, it changes to positive. The negative of a negative is positive. So I can do that. Notice if I flip this number, let me just write 2 to the 3x minus 5 first, and I flip 1 over 2 and write it as 2 over 1, which is just 2, that changes the exponent from a positive 17 to a negative 17. And now, by using this property here, I have rewritten this number as a base 2, and because of that, our exponents are now equal to each other. So the equation would be that 3x minus 5 equals negative 17. I would add 5 to both sides to get negative 12, divide by 3, and x equals negative 4. So this is the solution to this equation. Let's do another one using natural logs. Well, here, natural bases. Here, the same situation. Using the exact same property as the previous one, if I get the reciprocal of this, that changes the exponent again from a positive to a negative and a negative to a positive. Now, this notation is just written differently, but this means the exact same thing. That's why I wanted to go over this example right here, because having 1 over e to the 9th power is the same thing as 1 over e and the 9th power being up here. Because 1 can be raised to any power and you're still going to end up with 1. So we end up again with that. 1 to the 9th is still 1. E to the 9th is obviously e to the 9th. So using this property over here and getting the reciprocal of the right side, 1 over e, and write it as e over 1, that changes the exponent from a positive 9 to a negative 9. Now this one should also have a negative sign on that example right here. We should have a negative x squared there. So negative x squared equals negative 9. Since the bases are the same, the exponents are equal to each other. And to solve this equation, we start by first dividing by 1, negative 1. That makes the 9 positive. And to cancel out the square, we take the square root. So there's your solution. X equals to both positive and negative 3. Now, just like the last examples where we get the reciprocal so the bases become the same, we can do the exact same thing with these type of numbers or integers again that don't have the same base as this part right here. So notice that 5 and 25 obviously are not the same base. But if I look at the factors of 5 or the multiplicity of 5 and see that 5 to the second power is equal to 25, I can manipulate this number and rewrite this number as 5 to the second power. It's the equivalent value, okay, of 25. So I'm just rewriting this number as a base 5. And by doing that, I still have the same equation. I'm just changing the way this 5 looks. I'm sorry, this 25 looks. Instead of making it look like this, I'm making it look like this. It's still the exact same value. And because of that, our exponents are equal to each other because the bases are the same. So now 4x minus 26 equals 2, sorry. So adding 26 to both sides, that would be 28. Dividing by 4, we end up with positive 7. So x equals positive 7. Which reminds me, let me check an answer that we wrote in this one. Yeah, a negative 4. I wasn't too sure if I wrote negative 4 for this example. Yeah, but that should be negative 4. Okay. So let's look at this one. So here, obviously, having 1 over 64 and 4 are not the same base. So the first thing I want to do is flip this because I want the bases not to be, the only way to get an integer and this to be the same is if this is also an integer. So I'm going to write this as 64, and that changes the exponents to negative 1. Now the bases are still not the same value. But again, if I'm familiar with my multiplicities of 4 and my multiplication table, 4 to the second power is 64, and 4 to the third power multiplies 3 4s, which is 64. I'm sorry, 16 first. 4 to the second power is 16, but 4 to the third power is 64. So if I use this substitution and write 64 as a base 4 to the third, then that satisfies the condition of the 1-to-1 property. So 4 to the third raised to the negative 1. Okay, so I'm simply replacing this with that. Now I'm going to apply another exponential property here and review again this property, that if I have a base and I raise it to a power and then raise it to another power, I can simplify this by multiplying those exponents together. And that's exactly what I'm going to do here. So 4x squared minus 4 equals 4 to the negative 3 power. And now, with the bases being the same, our exponents are equal as well. So x squared minus 4 equals negative 3. We would add 4 to both sides, getting positive 1, taking the square roots. X equals to both positive and negative 1. And there's your solution. Now, the next example here is an example where the value of the smaller number or the larger number have to be both changed. So here, 4 to the second power is 16. There's no way to get 8 to be written as a base of 4 to some exponent. However, if I look at a different number, a number smaller than 4 and 8, for example 2, you should notice that's 2 to the second power is 4 and 2 to the third power is 8. So therefore, I can change both of these numbers to the following situation. 2 to the second power, that's going to be 4, but this is still raised to the x minus 4 power, and 8 can be written as 2 to the third power. Now again, using the same property from the last example, I can simplify this right here by multiplying these exponents together. So 2 to the second and then to the x minus 4 power is 2 to the 2x minus 8 power. And now the bases are the same. The exponents are equal to each other, and we end up with 2x minus 8 equals 3. We'll add the 8's to both sides, which is 11. Divide by 2. And it's 11 over 2. 11 divided by 2. 11 halves. Alright, let's look at another example like that. So similarly, here the first thing I want to do, again because this is a fraction, is get the reciprocal of this. Do not want fractions. So 9 to the 2x plus 14 equals 27 to the negative 1 power. But again, 9 to the second power equals 81. So there's no way to write 27 as a power or as a base of 9 to some exponent. However, again, being familiar with multiplication, 3 to the second power is 9, and 3 to the third power, multiplying 3 3's, well, that's 27. So I can change both of these numbers to base 3's. So 3 squared raised to the 2x plus 14 equals 3 to the third raised to the negative 1 power. And again, using the same our power of a power principle, we have 3 to the 4x plus 28 equals 3 to the negative 3 power. So now our bases are the same. And by the one-to-one property, that means the exponents have to be the same. We subtract the 28, as you see right there. Negative 3 minus 28 is negative 31. We will divide by 4. And x equals negative 31 over 4. And there you have it. So this is how you apply this one-to-one property. Now, this technique again works well when we're able to do this and find again a way of rewriting these bases to a common base. But let's say we can't do that, like in this example. In example number 9. There is no way of getting 5 to be written as 2 to some power. And well, 2 is a prime number, so there's no way of rewriting both of them, switching both of them, like we did the last several examples. So in this situation here, the way we solve them is by using the natural logarithm. Technically, well, this works for any equation. We can use this technique even on the previous ones, okay, which I'll come back to in a second and show you how this works even for these examples. But the way we use the natural logarithms is that we have to first make sure that the exponential expression is isolated. That means b to the x is the only thing that is on the left side or on the right side of our equation. So no adding anything to b to the x, none of that. No multiplying some number to b to the x. or subtracting or dividing. Okay, so we just want b to the x to be by itself. What we do then is that we take the natural logarithm of both. So we take the ln to b to the x and the ln of whatever the number is on the other side. And by doing that, we're going to use the following properties, one of the two following properties. If our base is not the natural base, we use our property of expanding the power property of expanding logs, and pull this to the front and write this as x times the natural log of base. And if the natural log of base is e, well, by doing this and writing x times the natural log of e, well, you'll remember when we're evaluating logs, ln of e is equal to 1. So we end up having x times 1, which gives us this value of x. So that's going to happen every single time if the base is e. This becomes 1, and then, but we're pulling this to the front. X times 1 is simply going to be x. And then we just simply have to solve for the equation for the variable x if like we're doing other stuff with it. So for example, going back to this example right here, like I said, there's no way of rewriting 5 as a base 2 or changing both of them so they have a common base. Remember, b can never equal to 1, and it's definitely has to be greater than 0, has to be a positive number. So here, we'll simply start by taking the natural log of both sides of this equation, and using again the power property of logs, we would pull this to the front, and x times the natural log of 2 equals the natural log of 5. Now, because I'm multiplying x with the natural log, the inverse operation here would be to divide by the natural log of 2. That reduces this. This becomes 1. And x equals to the natural log of 5 divided by the natural log of 2. So that's our solution. Now let's approximate what the value of this is. So we're going to take the natural log of 5, close the parentheses, and divide that by the natural log of 2. Hit enter, and that is 2.322. So that is our approximation. Let's do another example. So this one, same situation. We'll start by just taking the natural log of both sides. And here, and I'll only do this one time, this, remember, is equal to 1. So x times 1 is x. And we have the natural log of 10. But just to verify again, just so you know, the natural log of e to the first power again, because that's what it is, it's e to the first power, that's the invisible one right there. As you see again, that equals 1. And again, multiplying x with 1 is just going to be x. So our answer is that x equals the natural log of 10. Let's approximate that answer. 2.303 is the approximation. Let's do some more examples. Let's say that our exponential expression is not isolated. So look, here we have our exponent, here's our base, but it's not isolated. Notice that we're multiplying e to the x by 3. So the first thing we need to do is get rid of that multiplication and divide by 3. So e to the x equals 4. And now, with our exponential expression isolated, we can now take the natural log to both sides. And again, this right here is going to simplify to just x. So our answer is that x equals the natural log of 4. And let's evaluate that. The natural log of 4 is approximately 1.386. Same situation here. Our next example, our exponential expression is this one right here, because obviously it has the exponent x up there, so 4 to the x power. So what we need to do is get rid of this plus 9. So since we're adding 9, the inverse operation would subtract 9. So 4 to the x power equals, what's that, 6? So we would then take the natural log of 4 to the x equals the natural log of 6. We end up with this. We're going to divide by the natural log of 4. This becomes 1. And x equals the natural log of 6 over the natural log of 4. Which is approximately 1.292. And there you have it. Let's do a couple more examples, all right? Just so we could see different variations of how to isolate, again, this exponential expression before taking the natural log. So for this example here, we're multiplying. Our exponential expression is 6 to the 5 to the x power. So we want to isolate this. Again, because we're multiplying, the inverse operation is to divide. So 6 to the 5x power, that is 16. We're going to take the natural log of both sides. We're going to divide by the natural log of 6. And this reduces to 1. So we're left with the following equation. We have 5x equals the natural log of 16 divided by the natural log of 6. And let's approximate this answer. Let's see, what is this answer going to approximate to? So let's take the natural log of 16, divide that by the natural log of 6. And that approximates to 1.547. Now, that hasn't telling us again, we have not done yet because we still do not know the value of x. We're still missing that part there. So to figure out the value of x, let me move this over a little bit. Well, since we're multiplying by 5, we're going to divide by 5. That reduces this to a 1, and x is approximately 1.547 divided by 5. I have my answer there, so let me just divide my answer by 5. So that approximates to 0.3094, so 0.309. So this is our answer to this one. All right, let's look at the next example. On this example, again, our exponential expression is e to the x plus 5 power. And since we're subtracting 9, the inverse operation to that would be add 9. That way we isolate e to the x plus 5 power, and we end up with a total of 21. Taking the natural log of both sides, this, remember, is going to become 1. So since this is going to be pulled to the front, and again the blue part is 1, we end up with x plus 5 times 1. which is just simply x plus 5. And on the right side, we have the natural log of 21. So let's approximate the natural log of 21, which is 3.045. So 3.045. And to solve for x now, we subtract 5. So I'm just going to simply subtract my answer by 5. Instead of typing in the number, I already have my answer there on my calculator screen, and we end up with negative 1.955. And there's your answer. All right, we have a couple more examples, right? So in this example right here, again, the exponential part is this part right here. And we're doing two things to that exponential part. We are multiplying by 5. Here we go. We're multiplying by 5 and subtracting 4. Now you can get rid of the 5 by dividing by 5, but then you have to divide everything by 5, giving us fractions here, and let's not do that. So let's start by first eliminating the 4. So we'll add 4 to both sides. Giving us a total of 30. And now, if I divide by 5, this reduces, and 7 to the x plus 2 power is going to equal to 6. And that's easier to work with than having to get this fraction here of dividing by 5 first and then end up with fractions and then moving that over. You'll still end up with the number 6, but you end up again with fractions, and I know how much we don't like working with those. So we end up now with this. Now if I take the natural log of both sides, we end up with x plus 2 pulled to the front times the natural log of 7 equals the natural log of 6. I kind of did 2 steps at once. Okay, I took the ln of both sides and automatically pulled this to the front. And that's how I got that. And of course, well, the right side is just natural log of 6. So here, I would start by dividing the natural log of 7. So I can isolate the parentheses part. This again reduces to 1. And x plus 2 equals the ln of 6 divided by the ln of 7. And let's approximate that value. We're going to subtract 2, so let me just subtract 2 from my answer, and x equals negative 1.0792, so this is your approximation. So there you have it. Let's look at some more examples, just one more example. So here another natural base. So here's our exponential expression, and we're subtracting 1, so let's add 1 to both sides. And now taking the natural log, that's going to pull this to the front, but since this is equal to 1, this multiplied with 1 is equal to 5x plus 7. And that is now the natural log of 10. Now let's evaluate the natural log of 10. So let's see what ln of 10 is. So ln of 10 is 2.302. So here we're going to subtract 7 from both sides. So let me just subtract 7 from my answer. That's negative 4.697. And then we're going to divide by 5. So let me divide my answer by 5. And we end up with negative 0.939. So that's the approximated value. And there you have it. Now, like I mentioned, we can use this method on any exponential equation, okay? Even if there's a way of changing the basis and making the basis the same, like on the last example that we did. Let's say we have this one right here, okay? So instead of doing it like this, let's simply take the natural log of both sides. So we have that. Dividing by the natural log of 9, 2x plus 14 equals the natural log of 1 over 27 divided by the natural log of 9. And now let's use our calculator and figure out what that is. So let's plug this here into our calculator. So the natural log of 1 over 27, close the parentheses, and divide that by the natural log of 9. That's negative 1.5. So we get exactly negative 1.5. So we will then subtract 14. So let's subtract 14 from our answer. Oops, hold on. No. So let's subtract, like I said, 14 from our answer. And that's negative 15.2. We'll divide by 2. And x equals negative 7.75. And there you have it. That's the solution to our equation, which we got negative 31 over, remember the answer to this was negative 31 over 4. So when I convert this into a fraction, I get the exact same value. Negative 31 over 4. So you see, I end up with the same solution. Using this different technique and not using the one-to-one property, I still end up with the same answer. So you can always use, again, this technique for every. The one-to-one property only works, again, in the special situations when there's a way of rewriting our basis so they are the same, and therefore our exponents would be the same. So on these examples, if you can't figure that out and can't find a way to make the bases the same, then you can use this technique every single time. Well, there you have it. So that concludes the examples on this lesson on solving exponential equations. If you have any questions, send me a message on Remind or through email. And like always, I appreciate you watching, and I hope you have a great day.